Thanks also to Sanjeev because he has sort of introduced the work I'm doing. It's quite close to what he's doing. So this has been done with Dr. Shamik Gupta, who is at Max Planck Institute at Dresden. And so it's the same problem as resetting as what Sanjeev had defined, but this time there are power laws. So again, he has in his introduction defined how you can look at it. It's sort of a search problem where you search randomly for some time and then suddenly return back. So you could think of it as searching for a pet or something. So this is a typical trajectory. So you have you have diffusion. So this is diffusion in one dimension. So x versus t graph, and so you diffuse for some time, and then suddenly at a randomly chosen time interval, you just choose to go back to, let's say, the starting point. And the question is, what happens in this system? So the broader context, again, Sanjeev has talked about it, is that you are considering continuously evolving stochastic processes which are interrupted by large changes at random times. And so this is one example that I would like to point out. So this is some work that I had done before. And in this case, the underlying process is an asymmetric exclusion process, which basically models mRNA and basically the protein making machinery where ribosomes load on mRNA, they move. And then what can happen is that even as this process is going on, suddenly the mRNA can decay and a new one takes its place. So it's the whole process itself, the mRNA itself is a dynamic thing. And then you can ask the question, what happens in this case? And this can be thought of as a process of resetting in which a lattice with a finite density is suddenly reset to a state which is zero density. Okay. Similarly, the example of search was all. Yes. Is all gone. Yes, that's right. So again, I mean, in search algorithms, as was pointed out by Sanjeev, one of the work. So the dynamical part of this work was already talked about in the previous talk. Yeah, for me, what is of interest is that this system always shows a power law. So this is diffusion, which is resetting, and the rate of resetting is constant. So the distribution of time between two consecutive resets is an exponential, and that is what he talked about. And there is a steady state. It's not the usual diffusion where you expand ad infinitum. You have a steady state, which is an exponential one, as was described. And there is another interesting property that the first passage time shows us minimum for a certain value of r, which is the exponential parameter. And there are many extensions of this have been done, and many other continuum dynamics have been studied. So what is common about all these things that have been studied before is that all of them consider a constant rate of reset. So the underlying distribution is an exponential. And what we have done is we have taken the distribution between two resets, the random time, as a power law. And so what is the motivation? Well, one is that power laws are fairly common. So these are sort of examples of systems where you see power law gaps between two successive events. I mean, neuronal firing, stock market, many things. And just from a purely theoretical point of view, power law has this thing that the consecutive moments start to become finite, from infinite to finite, as the power law exponent increases. So as alpha increases, when alpha is smaller than 1, the mean is infinite. When alpha is greater than 1, mean becomes infinite. For alpha smaller than 2, the second moment is infinite, and it becomes finite beyond 2, and so on. And therefore, we expect a very different behavior from what has been seen before. So the calculations is one thing that we have done is where do you find the particle at time t? And what it requires is that, so this is a process in which you lose all memory of what happened before the very last reset from this time. Okay. So what you should know is when was the last reset, and then from then on it's just a simple random walk propagator. And so one has to know this quantity to calculate p of x. But then for a memoryless process, for an exponential thing, this distribution is an exponential itself, but for a power law it takes a more complex form. So we have calculated this quantity here. So what one has to know is that what is the probability that there was a reset time at reset at the previous time tau before the time right now, and that's given by the product of these two. And the thing is, we can calculate it. So what we see is that this probability that the previous reset was at a time tau before the current time takes these two different forms for alpha smaller than 1 and alpha greater than 1. And one thing to notice is for in the alpha smaller than 1 form is that it has two peaks, one at tau equal to 0 and one at tau equal to t. That means very high number of resets, either very close to the time the random walk starts and very close to the time where you are measuring it. Okay, and okay, so then what you have to do is you have to plug it in and then do the calculations. And for alpha smaller than 1, this is the form we get. So what one should notice is that the form has an x square by t dependence, like diffusion. So there is no steady state for alpha smaller than 1. Okay, and the way one understands this is that because of the power law distribution here between two successive resets, the gap, the time between two successive resets, the mean of this one is infinite. Therefore, you have many situations in which two consecutive resets are very far from each other, therefore allowing the particle to go very fast. So you do not have a steady state for alpha smaller than 1, and you can look at the extreme behaviors, and there is something more interesting happening here. So if you look at the behavior at small x of this function, you see that there is a change from a cuspy behavior at alpha smaller than half and a divergence at alpha greater than half, and this was a bit of surprise. And the way one understands is that, as I had pointed out, that this function here, so this is the probability of having a reset at a time tau before the current time, and this has two peaks, and these peaks sort of shift in their importance as alpha is changed. So when alpha is large, the peak at time t, which is the current time, is more dominant. That means at around the time you are measuring, there is a reset. Very close to the time that you are measuring, there is a reset. So there is a very high probability at alpha greater than half for the particle to be found very close to the origin. Okay, so that's the way we understand this. And at large t, you sort of see the Gaussian. Alpha greater than 1, here the mean of the distribution between two successive resets becomes finite, and therefore one starts seeing time independent steady state at large times, similar to, I mean, at least at some level to what you see in the exponential case. And you have this incomplete gamma function here. So there is a steady state in this system. So there is a crossover. This is a second crossover that one sees at alpha equal to 1 from a non-steady state to a steady state. And then again, one can study the extremes in this case. And what one sees is a cusp at small x and a power law behavior at large x. Okay. So further, of course, the mean in this case is always 0 because there is a mirror symmetry in the dynamics basically. But there is something further interesting if one looks at the mean square displacement. So if one looks at it at alpha smaller than 1, where it goes as t, so infinite in the large time. At alpha larger than 1 but smaller than 2, where there is a steady state in the system, so there is a time independent, at large times there is a time independent probability. There is still a t dependence, so it's still infinity at large t, and at alpha greater than 2, it becomes finite. And so this part here is interesting because this is saying that although there is a steady state time independent probability distribution, the x square is still infinite at large times, and that's again to do with the property of the power law itself, because for alpha smaller than 2, again the second moment of the power law is infinite, and it becomes finite only at large t. So though you have a finite mean, you can go very, very far from the steady state distribution. That's what it's saying. We have also been able to calculate, see the mean first passage time. So this is the way it is calculated. So this one has a memory. So what one is asking is, what is the probability of passing a certain point for the first time at a certain given time? Okay. And so what one has to consider is, again, you consider that till the previous reset, the particle has not passed the point or the target. What is the probability of having the previous reset at that time? And then since then the particle has been doing a regular random walk, so you know this probability just from diffusion. And yeah, so this one can calculate not the full distribution here, but one can calculate the average of the distribution, and it takes this form. What is interesting here is that it shows a non-monotonic dependence. So this is the mean first passage time as a function of the power law exponent. So this is saying that at alpha equal to 1, this is diverging, which is sort of expected because you are going to a pre-diffusion type behavior. But there is a minimum at a given value of alpha. This was slightly unexpected. This happens in the case of exponentials, but power laws do not have a time scale. So, and at very large values of alpha, you go to a constant where basically there is a resetting after every constant time. That is the deterministic limit. And for alpha smaller than 1, as expected, the behavior is more diffusion-like, and the average time to reach a target is infinite. Okay, so to conclude, we studied this problem of diffusion with resetting at gaps that have power law distributed, and there are many crossovers that one sees here. So one is from a cusp to divergence at alpha equal to half. Then we see in this case that a steady state does not always exist. There is a crossover from a non-steady state to a steady state behavior. And again, there is another crossover when you look at the fluctuations at alpha equal to 2. And we see from the study of first passage times that the time to reach a target is minimum for a given value of alpha.
Maybe we can continue after the session. So let's thank Apoorva once again and all the other speakers.